Okay, so one of the applications we have of power series is evaluating sums that look like this. In this case, we're going to sum from 3 to infinity of n divided by 5 to the n. And this might not look much like a power series at first, so let's go ahead and rewrite it so that it maybe becomes a little more recognizable as a power series. So if I move the n off to the left-hand side, or to the left of it, I get this 1/5 to the n. And if you remember, power series take the form of like the sum of some coefficient x to the nth power. So we think about this as x to the n. And having 1/5 to the n here should make you also maybe think of geometric series. And that's a lot of times how we will start these problems, because we know how to evaluate geometric series. Remember that with your geometric series, that's the power series 1 over 1 minus x. And if we expand that, we get the sum as n goes from 0 to infinity of x to the n. And so if you look at this, so if we want to write that, so if we were able to find a power series of the form n going from 3 to infinity of n x to the n, then we could plug in x equals 1/5 and solve our problem. But we somehow need a way to get the n from our exponent into our coefficient. And the way we're going to do that is we're going to take a derivative. Because when we take the power rule, the n will come down into our coefficient, and the power will decrease by 1, but we'll deal with that problem when we get there. So the first thing we do is take the derivative of both sides. And by a miracle of analysis, we are able to differentiate power series term by term. Meaning that we can bring the derivative inside of our sum and evaluate this very simple power rule. So on the left-hand side, what we need to do is think about 1 over 1 minus x as 1 minus x to the minus first. And then we can apply a power rule. But we also have to remember our chain rule, which will give us a -1. So in the end, what we should end up with is 1 over 1 minus x all squared on the left-hand side. And on the right-hand side, what we'll end up with is a sum starting at 1, going to infinity, of n x to the n minus 1. And one way to think about why we start at n equals 1 rather than 0 here is because when n is 0, our coefficient is going to be 0, and thus that term doesn't show up in the sum anyway, so we might as well start at n equals 1. We also don't want to have to deal with x to the minus 1. That's one of the other issues that arises. So we're going to go ahead and start our sum at n equals 1 after we take our derivative. And so you'll notice that we have the n in the coefficient like we expect, but we have a couple issues. First and foremost, our sum doesn't start in the right place. And secondly, our coefficient seems a bit off. So both these problems we can deal with. The easiest problem to start, so you can start with either problem first, but the easiest one to probably start with would be to get this coefficient fixed, and then next to fix our index. And the logic behind this is that we want our template to match what we desire. And fortunately for us, we can multiply both sides of our equation here by x. We're allowed to multiply both sides by a constant with respect to n, and x is a constant with respect to n. Excuse me. So we get this sum here, starting at 1 going to infinity, n x to the n minus 1, And we're going to go ahead and we're going to bring this x inside of our sum. And like I said, x is a constant with respect to n, and so we are allowed to do this. And go to 1 to infinity. So x times x to the n minus 1 is going to be x to the n by our rules for exponents. And so now we've matched the right template that we're looking for, right? We've got ax to the n here and ax to the n here. Now we can deal with this n equals 1. And one thing we know about series is that we can pull out a finite number of terms and not affect the series. So, for example, here we start at 3 up here, but we start at 1 down here. So, a helpful way to think about this is we can pull off the first and the second term and then sum up everything else. And everything else will start at 3 and go to infinity. So you'll notice that when we do this, this is what we're looking for, right? We plug in 1/5, which we'll do here in a second once we figure out what these first two terms are. So when n equals 1, we get 1 times x to the 1, also known as x, right? Equals there. And when n equals 2, we get 2 times x squared, also known as 2x squared. Now we can go ahead and just do some straightforward algebra and move these two terms over to the left-hand side. And so, by doing that, what we end up with is x over the quantity 1 minus x quantity squared minus x minus 2x squared, and we know this is equal to the sum n going from 3 to infinity and x to the n. Now remember that we want to think about this 1/5 here as the value of x we want to plug in. So by plugging in 1/5, on the left-hand side we get 1/5 over 1 minus 1/5 all squared, minus 1/5, minus 2 times 1/5 squared equals the sum as n goes from 3 to infinity of 1/5 to the n. And now we can take our calculators or work out by hand what this sum is. And it turns out that sum is, let me check my notes, 13 over 400. When you simplify everything down, and this is the sum, again, n equals 3 to infinity, n times 1 over 5 to the n. And so now we've evaluated the sum. We have a finite number, and that's all we need to do.